quick fun fact for you.
Yeah.
For all the people out there angry about the fact that Dune has lasers and body shields, but they still fight with swords and knives. It's because if they use a laser and it hits a body shield, it causes a nuclear explosion on both ends.
Boom.
Boom. That's why
right.
they use swords.
Frank
All right,
Herbert thought of
people?
that. Nice try.
You know why he thought of that?
Why? He wanted to have
I learned
swords.
this. He didn't want to predict like computer tech in the future.
What?
Anyway, we're a Dune podcast now.
We're Dune Podcast. Yeah, we are.
Hi, everyone. Welcome to the Reference Frames Podcast, a physics podcast where myself and Will try to take your favorite physics concepts and your favorite not physics movies and morph them together. We take big scenes, we explain a physics concept, and we use that scene to teach the concept. It's great. It's very fun. If you haven't been here before, welcome. We apologize for Will's voice this week. The library was all out of microphones for him to rent.
True. I'm a poor grad student. I do not own a fancy microphone. I'm on my earbuds right now.
Yeah, so let's get right back into our favorite place, the corrections corner.
Woo! Correction zone.
Correction zone. We got two. We got two corrections, and I will go first. I think I misspoke in the last episode and made a comment about how the LASIK procedure shaves down your retina. That is incorrect. You do not want to shave down your retina. That'd be bad news for you. Instead, they shaved down a part of your cornea, which is at the front of your eye, as opposed to the back. So there you go. A little bit of a misspeak, which was pointed out to me.
Which I didn't even know. I've never had LASIK, so I did not catch you.
I had LASIK, so.
Yeah, and then also I was only half correct when we were talking about why they use green lasers at when you're looking at the night sky and trying to point out constellations. I said that it was because your eyes are more sensitive to green light, and that is true. That's part of it. But the other reason is that green light also scatters more in the atmosphere, and if you want to be able to see the light that's shooting out of the laser, it needs to scatter back into your eye. Right, because if the laser didn't scatter at all, you would never see it. It would just fly off into space, right? So in order for you to actually see the beam, it needs to scatter off the air and bounce into your eye, and then you can see, the laser beam. So that's the other reason they use green lasers over other colors. Which
is kind of like when you point a red laser pointer at something, you don't see it until it hits that thing.
Right, or unless it's a lot of dust in the air or something like that.
Dust or particles or fog machines.
Or a bunch of flour.
Like laser tag or a bunch of flour if you're in a bakery
French
laser fight. I don't know, man.
Yeah. You get it.
That's it, I think.
Nice.
That's the end of the correction zone.
Real smooth.
Yeah, a good transition out of that.
Smoothly.
It's in our rear view mirror now. Honk, honk.
Honk, honk.
The next part of our show, if you haven't been here before, I'll explain it again. Will read a narrative that describes a scene, and then I will take a guess as to what in that scene might be physics related that we could learn about today. And then we will learn about that thing. All right, Will, take it away.
All right. An interrupted coronation, a blazing comet overhead, and a confrontation between siblings long at odds. Azula, cruel but meticulous princess of the Fire Nation, challenges her long-exiled brother Zuko to an Agni Kai, a traditional firebending duel, for the title of Fire Lord. Their powers at a zenith due to the once-in-a-century comet lighting the sky a dusky red, the duel begins with Azula's infamous azure flames leaping out at her brother. Zuko dissipates the flames with his own yellow fire, and as the somber score plays, the two leap and pirouette in a dance of fire and emotion. Zuko knows his sister well, and can tell that something is off. Her ever-present veneer of hostile civility has cracked, and Azula has become off kilter. As she falls further into madness, her trademark blazes become wilder, as Zuko's control over his emotions lends his flames greater control as well. For the first time in his life, Zuko's yellow flames prove more powerful than his sister's blue. And after some underhanded tactics on Azula's part, it is nonetheless Zuko that is crowned Lord of the Fire Nation, while his sister twists and writhes in chains, pitiable in her uncontrollable roars and tears of rage. Alrighty, then. So that's the scene. Great scene. Excellent scene. What do you think we're talking about today?
Oh, wow. This is a tougher one, maybe.
Yeah, maybe.
Than you've normally given me.
Mm-hmm.
It's the comet. The rest of it was a red herring.
Aha, it's the Sozin's Comet.
From the very beginning.
It's not Sozin's Comet.
Man, I am kind of at a loss on this one. The colors, the flames are different colors, I guess. That's kind of interesting. Rockets. Are they using the firebending to rocket around?
Using the rocket equation. No. You were
All
closer a little bit ago. We're talking about...
I was close.
Yeah?
When I said there's no physics in firebending?
That's
when I said the colors of the flames.
The colors of the flames. We're talking about flame today, and specifically blue versus orange flame, different colors of flame, why they're different colors, how fire works.
Oh, how fun. That's not physics.
There's a surprising amount of physics. We're not going to talk about like the chemical reactions so much that make a fire, but we'll be talking about how we see a fire and how
That's good, because I'm not here for chemistry. Neither are our listeners.
No. I'm not a
chemist.
chemist.
That's just stamp collecting.
You shouldn't trust me when I'm talking about chemistry.
Cool. Yeah. All right.
Yeah. All right. So,
bring it on.
Yeah. All right. So a brief chemistry, just, get it out of the way. Just so I don't have to talk about it too much. Let's talk about just what a fire is in general, right? So,
yeah,
a fire is a chemical reaction. It's a fancy way of saying a fire is basically, it's our sensory experience of a chemical reaction known as combustion, which is where, you might know this from elementary school, or if you're like a Boy Scout or something, right? It's a mixture of heat, fuel, and oxygen, right? The three things you need for a fire. Those three things all together, you can get a chemical reaction known as combustion going, which we know of as fire. All right, so that's
I agree.
The most chemistry we'll be doing, I hope. What we're talking about specifically is the flames, which is just the visible part of a fire, the gaseous part of a fire. All right, so it's often said that blue flames are hotter than orange flames, right? Have you heard that before, Ian?
Yeah.
All right, well, it's not necessarily true.
What?
It's not.
I was lied to.
It can be true, but it's not always true. In fact, if you look at a candle flame, a lot of times you'll see, most of the candle flame is orange or yellow, but right at the wick, right at the very bottom of the flame, it'll often be blue, right? And at least according to Wikipedia, which I'll trust on this, that blue area of the flame is actually roughly 400 degrees Fahrenheit cooler than the middle of the orange part. So it's totally possible for blue flame, even in the same fire, to be cooler than orange. So it's not exactly a direct corollary between color and heat. All right.
Okay.
So a reasonable question you might ask then is, what does make flames different colors then? If it ain't
temperature, what is it?
Yeah. Why are some yellow? Why are some orange? Why are some blue? Right. And there's really two different phenomena at play here. Both nice physics phenomena. The first is known as black body radiation. And the second, we talked about last week, actually, on the laser episode, is the idea of emitted light from excited electrons when they're dropping down energy levels. So we'll talk about black body radiation first, and then we'll give a brief, recap primer of this emission as well. All right.
I'm hyped.
Yeah. All right. So black body radiation, it's the basic idea that if anything has any temperature above absolute zero, they are constantly emitting light. Any object that's above absolute zero, which is any object period, is always emitting some light. However, most of the light is invisible. It only becomes visible light. It gets into that wavelength regime roughly around 1,000 degrees Fahrenheit. That's roughly 800 Kelvin if you're a scientist. And that is like a dull red. So I actually learned this as I was researching this episode, but if you have like a piece of metal, like in a blacksmith shop or whatever, that's been heated just to that very beginning of giving off red light. If you look at it in a pure dark room, it actually looks like it's a glowing gray. It's pretty cool. The light that it's emitting is red light, but it's so dim that only your light receptors, not your color receptors in your eyes, actually can pick them up. So if it's cool enough but still hot enough to glow, you'll actually see it as gray in a dark room, which is kind of cool. Anyway, so it starts as red, and then it gets orange, yellow, eventually it gets white, and eventually it gets blue. The temperature ranges are pretty extreme. So like 1,000 Fahrenheit, we said, was when it gets a little bit of red. It becomes orange at like roughly 1,700 Fahrenheit, yellow at about 2,000, white at about 8,000, and blue at about 12,000 Fahrenheit.
That's a huge leap.
Yeah. Well, I kind of was looking at a spectrum, so I kind of picked where it looked white, where it looked blue, where it looked orange. So that's not exactly scientific, but you should note blue is roughly 10 times the Fahrenheit temperature of dull red. So quite a bit hotter, right?
Yeah.
Yeah. And so if you think about that, if you actually had a blue flame driven by this phenomena, black body radiation, it would be 12,000 degrees Fahrenheit, which is a little hotter than a candle wick bottom, if you can imagine that. So clearly, black body radiation is not causing the blue flames we often see, right?
No, it can't be.
Yeah.
Right?
Yeah, definitely isn't. So what is causing that? That's the second phenomena. And we'll talk about how this shows up in the actual flames after we get through both these different phenomena. So this whole emission spectral banding stuff is all about what we talked about last time with lasers, right? There are certain molecules or atoms, electrons can be excited to different energy levels. And when they drop back down to the original energy level, they give off that energy as light, right? And whatever color that light is depends on how much energy that electron got excited by. And if just you remember, blue light is a high energy, right? So there's a big energy gap from when it dropped below, and red light is low energy, right? So in flames, both of these phenomena can happen, both black body radiation and electron and photon emission, right? So for black body radiation, when you're burning something like a candle wick, right? You're burning a candle. There's a chemical reaction happening, right? We talked about that, this combustion reaction. Oxygen is reacting with the fuel in the candle, and it's creating CO2 and H2O in different proportions, whatever. A lot of this fuel, though, before it can react, is vaporized as carbon, right? It gets vaporized because it's so hot. It flutters up into the area where we see the flame. And if it isn't converted to CO2, they clump together as chunks of what we call soot and are heated up by the heat. And as we know, when things get heated up, right, like radiation says, if it's heated up, it starts to glow. And so all of the yellow orangish colors you typically see from a flame, like on a candle or a campfire, that is just the soot in the air as it's being tossed up, vaporized, heating up so much that it's glowing hot yellow and orange and red. Does that make sense?
Yeah. Actually, as a brief aside,
Mm-hmm.
a party trick you can do to see this in action.
Mm.
If you have a candle and a lighter and you're under direct adult supervision, you can blow out the candle and then light the smoke that is sort of wisping up, and you can relight that ash and that soot, and you can watch it travel back down the sort of smoke line back onto the candle to relight it.
That's true. Very cool. Because there's still some fuel in that, right? It's vaporized fuel.
Yeah. Mm-hmm.
Very cool. All right, so that's how we get the yellow light. But clearly these candles aren't 12,000 degrees Fahrenheit, so where the heck is that blue light coming from, right?
Yeah.
So as we talked about, there's a lot of chemistry going on here. There's a lot of chemical decomposition happening inside of that flame all the time. And if there is enough, so I said the black body radiation happens if there's carbon that isn't converted to CO2, right? If there's carbon left over, it clumps together as soot, it heats up. If there's enough oxygen, though, you won't have any excess carbon, right? If there's enough oxygen to turn all the carbon into CO2, then there's no remaining carbon to turn into soot and to glow and to, look like a flame, an orange flame. So if there's enough oxygen supplied, there won't be any soot. And as a result, there won't be any yellow light glowing. So what you see is not glowing soot, but you see is all of these different chemical reactions taking place, creating a lot of what are called molecular radicals, which is a little beyond my pay grade, but essentially it's a lot of carbon, larger molecules and things like that are missing some electrons, things like that. And they don't stick around for very long because they're very reactive, but they do stick around long enough during these chemical reaction chains for their excited electrons that they have because they're doing all these reactions But those electrons that drop down and emit light. And for typical fuels, like we see in candles and in wood, right, that energy emitted in the atoms that are being excited and the radicals that are being created, the molecules, that energy emitted is almost entirely in the blue range of light. So what we're seeing there isn't the soot glowing from heat. It's actually just all the electrons dropping down and emitting light of a certain frequency, in this case, of blue frequency. Several frequencies, but all of which are in the blue regime. Does that make sense?
Well, how about that?
Yeah.
Makes a lot of sense because I remember our last episode, which was about lasers, folks. Will's referenced it a couple times. If you're interested in lasers, you go check out our previous episode.
Yeah.
So you mean to tell me that you were just seeing a lot of chemical reactions that are predominantly emitting blue light?
Well, the chemical reactions aren't emitting them. Chemical reactions are producing these reactants that then will react again. But before they can react again, their electrons that are currently excited are dropping down, and those electrons are emitting the light.
Right.
Yeah.
Because when the electrons drop, they emit the photon.
Exactly. Just like a laser.
Huh. Yeah. No way.
And so really, the difference between a blue and a yellow flame is just how efficient it is or how much oxygen is present, right? Because a good, efficient flame, you want to create as much CO2. Like if the reaction is happening as much as it can, there won't be any leftover soot. Because the soot is basically like a byproduct of not having enough oxygen present. So an efficient flame should be blue. And that's why if you have a butane torch or you have like a stovetop, typically speaking, it looks blue. Just because if they're designed well, there won't be wasting a lot of the fuel, because that's wasted fuel if it's turning into soot.
Right.
Yeah. And it's worth pointing out, every flame, every candle or normal flame that we deal with, always has a blue flame inside of it. There's a blue flame and a yellow flame. The blue flame is just a lot less bright than the yellow flame, so we don't usually see it very well. The yellow flame kind of dominates what we see. But there are these radicals going on. They are emitting blue light inside of every fire. We just often see the yellow ones if there's all this soot that's glowing, kind of overdoing it.
Huh.
Yeah.
Well, isn't that something?
Pretty cool.
What you're saying is Azula was just a more efficient firebender.
Yeah, and this is actually really interesting, right? So let's talk about that scene. So Azula, if you've seen the show, as a character is all about, ruthless efficiency, right? She's brutal, quick, cruel, right?
Cold, calculated.
Exactly. And so clearly, right, it seems, and I don't know if the showrunners were thinking this much about it, but clearly she has spent time and effort making sure her flames are as perfect as she thinks she is, right? She's all about perfection, right?
Yeah.
So she's probably spent all this effort making sure her flames didn't waste any fuel, whatever, right? Zuko, right, we know, isn't bothered by trying to be perfect. It's not really his character. And thus his flames aren't as efficient or clean burning as Azula's, because they don't need to be, because as we can see, he can be a better firebender even with less efficient flames.
Wow.
Yeah. So it's almost like a cool character study too.
Yeah. You didn't tell me we were going to do all of this today.
Oh yeah. All right. So that's kind of the scene, and that's kind of the physics here. So let's talk about either blackbody radiation or fires or, electron orbital dropping. Like, where do we see that in the world today? What do you think, Ian?
Here's a fun one. My coworker recently won a culinary torch in a drawing.
What?
Yeah. Like one you would
like
use
a creme brulee.
Yeah, exactly.
That's fun.
And it has a little knob on the back to control the mixture of gas or air.
Oh, sure.
And if she turns it all the way to the air side, well, I don't know which side, one side or the other, she starves it for air, then it would become yellower.
It should, yeah.
Yeah, and it gets longer and more flamey, right?
Right.
The flames start licking towards the ceiling.
Right.
As she goes the other way, it gets shorter, it gets more
concentrated,
afterburnery, and looks like a jet, like a,
Right.
So,
yeah, because in that case, it's very efficient. There's enough oxygen to react with all the carbon being created by the fuel.
Yeah. Another place, maybe this is a whole episode on its own, but black body radiation is quite important for astronomers. The apparent brightness of a star tells us its temperature, which can tell us...
Or the color tells us its temperature, because remember, black body radiation.
Your turn.
Oh, okay. Yeah. So where do we see fire today's? Well, California almost every summer it feels like.
Got him.
Got him. Sorry,
And
California.
that's its whole own thing, naturalism.
That's true.
Or conservationism, excuse me.
But black body radiation, though, we see it all the time. Not as much anymore, perhaps, but like all old school, quote unquote, incandescent light bulbs, right? That's just heating up the filament so much that it glows bright yellow, right? That's how light bulbs used to work. Nowadays, we have halogen bulbs and we have fluorescent bulbs and LED bulbs. And we can talk about some of that stuff later, maybe on a different episode. Those are really cool on their own. Very different functionality. They work very differently, but they all provide light.
Blacksmiths.
Blacksmiths. Yeah, actually, this one's kind of similar. Welding masks. Why do we use welding masks when you're welding something, right? You have the big piece of metal with the big lens on it that blocks so much light. Because you're heating this stuff up to such high temperatures, it's emitting all this white light right in your face, right? So you got to wear that mask to protect your eyes. And
it's like very strong sunglasses.
Exactly, like way strong sunglasses. And then the third one I have for radiation, black body radiation, is like night vision goggles, right? So infrared goggles, right? As I said, everything gives off light. Just generally speaking, it's not visible. It's not visible in the visible range. But if you have a detector that can measure infrared light, which is light of a lower energy, right? You can actually see things, right? You're basically seeing how hot things are with these night vision goggles. So that's the third and final one I got for that. Kind of fun.
Those are becoming more consumer available too. You can actually get infrared cameras that will hook into your iPhone.
That's right. I forgot about that.
So they're growing increasingly accessible in case anyone wants to play around with them.
Yeah.
And this is a tangent, but my favorite thing ever. You take a piece of glass.
Okay.
And you look at someone through the infrared, and they put the glass in front of their face, and they disappear.
Whoa!
Ooh.
Actually, yeah. You know what? Actually, there's a question that we got asked that's actually really related to that idea, which maybe we should ask. Maybe we should answer.
You want to answer that question instead?
Maybe. Yeah, let's answer that one instead. Since you brought it up, a nice little segue into Wi-Fi.
Okay. Well, that's all we have about today's lesson, I suppose. Tweet us your examples of black body radiation. I want to hear it.
Yeah.
Or your fan art of Will as Zuko and me as Azula.
No, other way around for sure.
What?
Yeah, I'm definitely.
Whichever one you feel is most correct.
Yeah.
Please.
If you want to be Katara, you can be Katara in the scene too.
Ooh, I would be a mean Katara. So let's move on to our questions. We are growing our backlog of questions. So thank you everyone who has sent us any.
Thank you very
if
much.
you'd like to send us some, you can tweet at us at Podcast Frames. You can also email us referenceframespodcast@gmail.com. If you know us in real life, you can come find us and we'll tell you to do that.
That's true.
I actually don't have those
remember
things.
I do not have those addresses memorized, so don't ask me.
It's just the name of our podcast at gmail.com.
Fair enough. I'll work on that.
That's your homework for next time. Try to remember the name of our email and Twitter account.
Will do.
So this week, the question we will be answering is from the mysteriously named Auric.
Wait, how's that spelled?
Auric?
How's that spelled?
Auric.
Ian, do you know that's the name of Goldfinger?
What?
That's Goldfinger's first name. We're getting Goldfinger from the last episode is emailing us.
How about that?
That's amazing.
What a delight. What a treat. Thank you.
Thank you, Goldfinger,
for your
asking
email.
a question.
And they say, how does Wi-Fi work? Or more succinctly and less vague, how does it work through walls?
Oh, great question, Alric. Thank you. I'm amazed you had Wi-Fi in 1960, whatever it was.
Dude was cutting edge with lasers.
That's a good point. That's a good point. So actually, yes, the reason I think we should do this one is it's similar to what Ian just brought up with this glass and IR and like blocking, not being able to see. All of a sudden, the glass is no longer transparent. Because that's
IR, of course, standing for infrared.
Thank you very much. I apologize. So you look at a piece of glass, right? It's transparent. You can see through windows. That's kind of the important reason we have windows made out of glass, right? But just like Ian said, it's only transparent for some light, right? So just like you said, infrared light is blocked by many windows, and UV light is also blocked by many windows. And those are the same thing as light, just different wavelengths than the visible light we're able to see, right? And so we call that transparency, right? So windows are transparent to visible light, but they're opaque to other types of light. All right. Same thing with any substance, any material, right, is transparent to some wavelengths and not to others. So, for example, X-ray imaging, right? X-rays are very high energy light. And as we all know, they pass straight through things, right? That's why Superman can see through walls, right? X-ray vision. And so in that case, the wall is transparent to X-rays. They travel straight through it. They don't get stopped. If you saw with X-ray eyes, you would be able to see through walls, right? Unless it's made out of lead, in which case, sorry. The same thing is true with Wi-Fi, right? So Wi-Fi, it's not perfectly transparent, but many walls, wood, things like that, as long as it's not too thick, it is quote unquote transparent to Wi-Fi, because Wi-Fi is, again, transmitted through light. It's radio waves in Wi-Fi's case, right? Different frequencies of radio waves. And for that wavelength of light, walls are practically transparent. So walls are basically windows for Wi-Fi.
You heard it here first, folks.
I hope that answers your question, Rick.
Walls are windows for Wi-Fi.
How about that? www.referenceframespodcast@gmail.com.
Why would you? It's an email. Why would you put a www in there?
Windows, Wi-Fi, and what was the other one? Anyway,
moving on.
Yeah, moving on.
Thank you for the questions. Send us all of your physics questions. They could be related to the episode. They could be not related to the episode. Whatever you want. We're happy to discuss. Additionally, send us your corrections if we did something wrong.
I'm not a chemist, so please tell us if I did my chemistry wrong.
We don't like to be wrong, but moreover, we don't like to continue to be wrong.
Exactly. We don't like to share wrong things without correcting ourselves.
No, that's bad news. If you want to get in touch with us, we've said it 80 times now at Podcast Frames on Twitter and referenceframespodcast@gmail.com. That's our email account. We don't have any ads or any way to spread the information about this podcast. So if you like it, it would be just a treat and a half if you sent it to your friends. It would bring a smile to Will's face. Huge update, folks. We peaked at number 11.
Oh!
We're climbing those charts. We're back down to like 47, but hey, we peaked at 11.
Well, we did take a few weeks off for various reasons, so we'll be back up there. Number 1 is coming.
We're coming for you, CERN. You got anything to say to our valuable listeners before we sign off?
No, I hope you enjoyed the episode. I had fun talking about it. I love Avatar: Last Airbender.
Thanks for listening, and we hope we'll see you next time.
See you later.